Hello everyone, my name is Aditya Lahiri and I'm here to present our work on combining counterfactuals with Shapley values to explain image models in the RDMDE workshop taking place in this year's ICML. This is joint work with Kamran Alipur, Ehsan Adeli and Babak Salimi with affiliations belonging to UC San Diego and Stanford University. Let us get started. First, let us discuss briefly the need for responsible computer vision. In recent times, many machine learning and deep learning models trained on massive image datasets have become widespread in their use. They are deployed across critical systems such as autonomous driving, law enforcement, and medical applications. These models impact humans who are on the receiving end of their decision making. Hence, understanding the decision making process behind these models and investigating their behavior is necessary to ensure trust and fairness of these models. Explainable AI, or XAI for short, attempts to fulfill this purpose. There has been considerable progress made in XAI for models trained on tabular datasets. Shapley values have emerged as one of the most popular and principal methods to assign feature attributions as a way to explain a model's decision making. Let us consider an example. Rosa is a customer of a bank that employs ML models as part of its decision-making process to grant loan to its customers. Here, the model predicts if an individual would earn less than 50K per year depending on their attributes. We note that the average probability of this decision is 0.5. We see that the black box model states that Rosa has a probability of 0.83 of making less than 50K. Shapley values allow us to decompose the difference between Rosa's outcome and the average outcome from the model among the individual feature attributes of Rosa. This is ensured by the efficiency property. Further, these attributions are also useful as they state sufficient conditions for when the feature attribution would be zero for any specific feature through the null axiom, and also ensures that for two features that behave similarly, they get similar attributions through the symmetry axiom. However, there are some issues in directly applying Shapley value-based feature attributions to models trained on image data. First, images are based on pixels in an atomic level, which makes images very high dimensional and non-interpretable. Even if we get attributions based on each pixel, they won't help the end user, for example, an auditor, understand the model behavior. This also increases runtime since Shapley values are exponential in number of input features. Secondly, Shapley value-based explanations are not contrastive in nature. For an explanation to be more useful to the user, it should be in contrast to another similar user who had a separate outcome from what they had to help them understand about their outcome better. This is not supported by current Shapley value-based frameworks by default because Shapley values explain the difference in outcome from the average outcome of the model, and there is often no meaning to an instance of averages. In our work, we seek to provide solutions for these two issues. First, we define input features in the image in terms of high-level human interpretable features. For example, for a model working on human faces, we define annotated high-level features such as age, blonde hair, makeup, and so on. This helps the end user understand explanation in terms of these intuitive features. It also reduces dimensionality and therefore runtime drastically. Second, we make Shapley value-based attributions contrastive. We do this by generating a counterfactual instance from the original instance using a novel shift predictor algorithm. We then replace the average instance by this counterfactual and use Shapley values to explain the difference between these two images in terms of above-mentioned high-level attributes. We now look at our experiments and a few results that are obtained. First, a disclaimer that this is not our data nor our classifier. In this work, we just want to provide explanations. We only use this setting to show how models can be biased and how they can be explained. Personally, all the authors do not endorse labeling subjective measures. Given this disclaimer, we want to understand the behavior of a deep learning model trained on VGG backbone on the A dataset. The target label is attractiveness, and 5 high-level attributes are used to explain the decision making. We have a set of original image O sub I, and we generate counterfactual images corresponding to each original image C sub I. These counterfactual images are generated by the user according to their own needs by increasing or decreasing high-level attributes in the original image. For instance, given original image O1, the counterfactual C1 in the first row was generated by decreasing youngness and makeup and blonde hair while increasing the attributes of baldness and maleness. This is made possible by our shift predictor algorithm. Now, we use Shapley value-based attribution to explain the difference between target labels for each pair of images in terms of high-level attributes. For instance, we can see that for a pair of images with index 1, increasing baldness was most important in reducing the target label of attractiveness, while decreasing youngness was the second most important reason. As next steps, we would like to incorporate causal graphs in our pipeline. Since Shapley values are expensive to compute, we would like to work on a more optimized algorithm. Thank you for listening to our presentation.